Okay, here is the third and final video in this set and for the semester. So we've got a guy holding a dumbbell and he's on some kind of rotating platform, and you've seen this kind of thing before. You've probably done it on the playground when you were a kid and swing on a swing set or something. You know, you spin around, you pull your arms in, you can go faster and that sort of thing. So this guy is doing that. And what we want to do is be able to just say, okay, how fast was he going? So how fast is he going to go once he pulls everything in? Okay. Now, this is extremely straightforward and extremely frustrating. Okay. So I'm actually going to work this one out in this little corner here. Hopefully it's not too tiny, because all we've got is that our initial angular momentum has to be equal to our final angular momentum. And that means that we've got some initial moment of inertia, omega I, and that's got to be omega final, I times omega final. Okay. Now, once we do our algebra, we're going to see that that final rotational velocity is just the initial times the ratio of the initial to the final. That's it. That's all there is to it. Boom. So if we get those I values, then we're good to go. Okay. That's the simple part, what I've just shown you. The harder part is how do we get those moments of inertia? Okay. This has a lot of components to it, and I'm going to try and break it down as simply as I can for you. And the simplest place to start is actually at the end. Okay, let's get the final moment of inertia first. And so what we're going to do is we're going to say that the final moment of inertia is equal, oops, I don't know why I put initial in there. That final is equal to two pieces. Okay, well, more than that, really. Okay, we're going to say it's the guy's torso and arms, which is a particular moment of inertia. So I tell you what, I'm going to call that, well, I'll call it I final 1. Okay, and then plus the moments of inertia of the dumbbells. Okay, now each of these dumbbells has 2 spheres, just like this. Okay, so we have a total of 4 spheres. So we're really going to have 4, we call it I final 2 for the spheres. Okay, and so let's see if we can break that down a little bit more. So I final 1. Okay, now it tells us to treat this as if his body is like a cylinder. So we're going to have 1/2, we call it MF1 RF1 squared. Okay, so that's a half, and he's 80 kilograms in that position, and his distance, oops, sorry about that, guys. His distance is 0.45, his radius rather, over 2. Okay, now we have to do that because they give us a diameter instead of a radius. Okay, but that's what we got to deal with. And when you do that, what you're going to get for that particular term is 2.025. Okay. Now let's find the other one. So IF2. Okay. Each one of those, it says that each ball is of negligible size. which is code for ignore the geometry. Treat it as a point mass object, which means we're looking at M F2 and RF2 squared. The mass of each one of those is 5, and the distance it's out there is 0.3. Okay. Now it's easy to miss that. Okay. But so study your drawing carefully. So in the final position, there, that's how far we are from the axis. Okay. And once you do that, then the number that you're going to get is 0.45. Just like that. Okay. Now, when I add all those things together, my IF1, 4 of my IF2s, then I can get what the final moment of inertia is for my system. And as a number, that's 3.825. Okay. Now, your numbers in the problem might be different. Okay. And so you'll have to just kind of go through that. Take your time. Don't get in a rush. Okay. There's a lot of details that you can mess up on. Okay. Now, let's go back and do the initial angular momentum. And we'll do it the same way, which is to say we'll do it in pieces. But it's got 3 different pieces that we got to work with. So we're going to have the balls. Okay, we got 4 balls out there. We're going to have arm pieces. And then we've got torso. Okay, so we're going to have 3 different pieces. 4 balls, 2 arms, 1 torso. Okay, so initial is, let's say, I'll call his torso I1, and then we got 2 arms. I'll call that I2, and then we've got 4 balls on the dumbbell. We'll call that I3. All right, I1 says to treat it like a cylinder. So we've got 1/2 M R, I'll call R1 squared, M1 R1 squared. Okay, and so that's 1/2. 68 is the mass of his torso. It's different than above because we're going to count his arms separately. Above, we counted his arms as part of his torso. And then R1 here is the radius of his torso, which they tell us is 0.4 as a diameter. So we've got to divide that by 2. And once we do that, we're going to get 1.36. Okay, now let's do I2. I2 is his arms. I2 is a little bit more complicated. We're going to have the geometry term for his arms, which is 1/12 into, let's call it L squared. That's the length of his arms. And then we're going to have an offset term, which is going to be M2. And the offset in this case is we got to get to the shoulder, and then we got to go halfway down his arm. So 0.65 over 2 squared. Okay, and once you run all of those numbers, the mass is just 6 on those things. What you're going to get is 1.865. And we got another one of those things where that moment of inertia of the 6 kilogram object is much higher than, or significantly higher than for the his whole torso, which has a mass of 68. Okay, but that's just, it's out there further from the axis of rotation, and that's what happens. It goes as r squared. Okay, I3. Okay, so this is just one of the balls. All right, and the balls are out there at a certain distance. So I'm going to go ahead and call it M3 just to make it easier. And the balls are out there at a distance of 0.2 2 plus 0.65. All right, so since we're treating them as a point mass, we just use mr squared. Okay, running the numbers on those, you're going to get 3.6125. Okay. All right, so we got our numbers. We only need one of those. We need two of those. And we need four of those. Okay. If we could combine them up, what we're going to get then for our initial angular momentum is 19.542. Okay. 19.542. All right. So now let's go back to where we started. Okay, so this thing was going at a half a revolution per second. Okay, and then we're going to multiply the initial angular momentum, 19,542. The final angular momentum is 3.825. And you can see he speeds up quite a bit, 2.555. And that's not radians per second, it's revolutions per second. Okay, which is one reason I like to write things in this form. Because I know that whatever units I've got for omega I will have those units for omega f, because it's just I over I. The units are going to cancel out. It's just a ratio. Okay. And anyway, there we go. He ends up going about 5 times faster. All right. So it's kind of cool. You can make yourself dizzy that way. Little kids love to do that. Okie dokie. There we go, guys.